Equilibrium is defined as a dynamic state of a chemical reaction where the rate of the forward reaction is equal to the rate of the reverse reaction. So if we have reactants being converted to products and then products being converted back to the reactants, the rate of the forward reaction, reactants going to products, is going to equal the rate of products going to reactants. At equilibrium, you would have both reactants and products present, but not necessarily in equal concentrations. This happens in a closed system. So if we're plotting concentration versus time, if we start with a certain concentration for reactants, over time it'll decrease until it reaches its equilibrium concentration. If we start with no products or very little products, over time it will increase until it reaches its equilibrium concentration. The dynamic part of dynamic equilibrium. Dynamic means changing. So the reaction doesn't stop when equilibrium is reached. But however, reactants keep changing into products and products keep changing into reactants. It just happens at the same rate. But reactions do not stop when equilibrium is reached. So if we want to calculate equilibrium concentrations for reversible reactions, when reversible reactions achieve equilibrium, before all the reactants become products, stoichiometry is very difficult to do. So we are going to do these calculations using an ICE table. So ICE stands for, the I is initial concentration. This is our concentration before equilibrium is reached. This is what happens at the beginning of our problem. C stands for the change in concentration. So this is the change that the initial concentration is going to have to do in order to reach its equilibrium concentration. Finally, E stands for the concentration at equilibrium. So our example here, we've got hydrogen fluoride forms its elements at SATP. We have initial concentrations of H2 and F2 and no HF. And then we're asked to calculate the concentrations of H2 and HF at equilibrium if the equilibrium concentration of F2 is 0.24 moles per liter. First thing, any equilibrium problem, we are going to write out a balanced chemical equation. We're going to use our double arrows to show that it's reversible. Second thing we want to do, set up an ICE table. Initial concentrations of H2 and concentrations always go into our ICE tables. So for H2 and F2, it's 1.00, HF is 0. Now we don't know how much the change is going to be, but we're going to say let X represent the change in concentration of the reactants or the products to reach equilibrium. These are going to change based on stoichiometric ratios. So products, because we have all products, all reactants, no products, the only way for our concentrations of our reactants to change is to go down to reach equilibrium. So we're going to use negative signs for the change in the concentration of reactants. We're going to add in the coefficient. So the coefficient here is only 1 in our balanced chemical reaction. So this H2 concentration is going to change by minus 1x. There's a 1 in front of F2 as well, so it's going to change by minus 1x. And HF, because it's got a 2 in front, it's going to go up because it's a product, and it's going to go up by 2 times x. and that's because of stoichiometric ratios. Our E column is just adding our I and our C together. So we're going to have 1.00 minus 1x for both H2 and F2, and just 2x for HF. The problem gives us, though, that this concentration here at equilibrium is 0.24 moles per liter. So we can figure out what X is by solving this equation. So if we do that, X is 0.76, and these are always concentrations, so moles per decimeter cubed. We can now figure out what the equilibrium concentration of H2 and HF is by substituting in the X value that we just found. So for H2, at equilibrium, it's going to be 1.00 minus 0.24, or sorry, 0.76. So it's going to be 0.24 moles per decimeter cubed. And the concentration of HF at equilibrium is going to be 2 times X, because that's what we've got here in our ICE table. So 2 times 0.76 gives us 1.52 moles per decimeter cubed.